This is Mr. Barron, and I'll be showing you how to solve problem number 35 and 39 in chapter 14. For problem number 35 in the textbook, which chapter 14 is on page 620, they tell you that you have a decomposition chemical reaction. SO2Cl2 as a gas is decomposing into sulfur dioxide and chlorine gas. And the good news is that they tell you the order of the reaction. So that information is already given to you. And then they tell you what the half-life is at a particular temperature. So the half-life of this reaction is 2.3 times 10 to the 5th seconds. All right, to solve this problem, we have to look up the equations for half-life. They can be derived from the original equations in our textbook, but what you want to do is just pick them out from the reading. For a first-order reaction like this one, half-life is equal to the negative natural log of 1/2 divided by k. Well, if you take the natural log of 1/2 and change the sign, you end up with 0.693 over k. So this is actually the equation we're going to be using to solve this problem, since it's a first-order reaction. Just as a side note, if it is a second-order reaction, which this reaction is not, half-life is equal to 1 over k times the initial concentration of your reactant that you're studying. So I'm going to use this one because we're working, of course, with a first-order reaction, and the question is asking for what is the rate constant. So the rate constant is k. So let me go ahead and write out my equation. And I usually like to get my unknown by itself first. So I'm going to rearrange this equation algebraically so that k is all by itself. And when I do that, this is the equation that I'm going to use to solve the problem. All right, now what I'm going to do is I'm going to plug in my given information. And my given information is up here at the top. That's my half-life. So k is equal to 0.693 divided by the half-life, which is 2.3 times 10 to the 5th seconds. And then you'll get your answer in k, or I mean your answer for k, which is going to be in inverse seconds. So I'm going to go ahead and type that into my calculator, which is 0.693 divided by 2.3 E5, and you end up with 3.0 times 10 to the negative 6 inverse seconds. And that's your correct answer for k. Now what we're going to do is we're going to transition to solving problem number 39. In problem number 39, you're actually working with the exact same reaction. This time you're given a data table. I'm going to go ahead and quickly construct the data table that you're given. You have time, which is of course recorded in seconds, and then you're given units of pressure in atmospheres for the initial reactant. And again, this is the same equation where we're studying this compound here decomposing into sulfur dioxide gas and chlorine gas. All right, I'm going to go ahead and quickly sketch out the data that we have. You're measuring at different intervals of time what the pressure is. Now the good news is, because of the gas unit that we've already studied, we know that pressure is proportional to our concentration, or at least changes in concentration. So normally we have molarity that we're looking at over time. We have pressure this time, and the pressure can be substituted in for molarity in any of the work that we're doing here. All right, so now I'm given this data here, and what I need to figure out is the question's asking me to figure out the rate constant, so I'm trying to find k. So let me quickly just draft out a rate law here. So the rate is equal to k times the change in concentration, or the concentration of SO2Cl2, and it's first order, so I don't have any exponent because it should just be 1. Now remember, pressure is interchangeable for concentration, so we don't have to worry about doing any conversions at all. Now, if I look at this, I could calculate, I don't have enough information to use this equation to solve it. But fortunately, I do have enough information on my formula sheet. Since it's a first order reaction, I know that this right here is the integrated rate law for first order reactions. The one below it is for second order reactions. So I'm going to use the one for the first order reaction. And what's cool about this integrated rate law, the natural log of the concentration of A at time t minus the natural log of the concentration of A at the starting point is equal to negative kt. What's cool about this is that you can literally rearrange it to get y equals mx plus b, and you can get a plot. So I'm going to add the natural log of A at the starting point to both sides a little typo there. All right, now what I'm going to do is I'm going to rewrite this equation. So it's going to be the natural log of A at time t is equal to negative kt plus the natural log of A sub down. All right, so when I look at this, what's cool about it is that this is y, that's m, that's x, and this right here is b. So m is, of course, our slope, and if I figure out what the slope is, if I'm plotting a graph where I'm taking the natural log of my concentrations, and this is going to be, so on my x-axis will be time, on my y-axis is actually going to be the natural log of all the concentrations, and then the y-intercept is, of course, going to be the very first point. So let me go to my graph, or my table, sorry, and I'm going to take all of these pressures and take the natural log of all of those pressures. So natural log of 1 is 0. Natural log of 0.947 is negative 0.0545. Natural log of 0.895 is negative 0.111, and so forth. And I'll continue to get all my calculations written out here. All right, so remember the most important thing about figuring out whether something's first order or second order, even though you're told it's first order in this reaction, if you take either your concentrations at each time interval or you take pressures, and then what you do is take the natural log of either of those pressures or those concentrations, and then you plot this on your y-axis, then you plot this on your x-axis, you should get a straight line. All first order reactions will be a linear plot if you do that. So now what I'm going to do is I'm going to go ahead and construct a graph where I have time on the x-axis, and on the y-axis I'll have the natural log of all the pressures. When I do that, I'll have 0 at the top, which is my y-intercept. So remember, at your very first concentration, let me show the very bottom down here. At your very first concentration, this guy right here, should be at so I'll look up here, my very first, the natural log of it, at time 0, my y-intercept will be 0. And then the values start going down from there. So goes down into negative values, then I'm going to plot this out, and then my time, of course, here's 0, and then I can make it out at regular intervals. This one will be 2,500 seconds, this one's 5,000, and so forth. When you plot it out, you get a straight line going down like that. So again, just as a reminder, this is my x, this is my y-axis. When you get that plot, if you find the slope is equal to k. So again, the way I figured this out is by rearranging that equation. Let me point to where I got that equation. The first integrated rate law equation for first order reactions. And by rearranging it and showing that that's my slope, that's my x, that's my y. This only works for first order reactions. You have a different equation that you use when you're dealing with second order reactions. For second order reactions, you're going to use that one below it, because if for a second order reaction, you get a straight line if you plot the inverse. So 1 over the change or the concentration, as opposed to the natural log of the concentrations that you're dealing with. And again, pressure is interchangeable for concentration. You can swap it in. The answer that you get after you figure out the slope for this, you find out that the slope, K, is going to be negative 2.19 times 10 to the negative 5th inverse seconds.